All right, in this video 9.5, we are going to talk about counting principles. They're going to talk about the addition principle and the multiplication principle, but really what we're talking about is ands and ors, which you have probably talked about in some way with Venn diagrams with what we call unions. So an or in math is equivalent to, if we say, probability of A or B. These are logically equivalent. And if we said the probability of A intersect B, logically equivalent to. Okay, so really that X is an element of set A or X is an element of set B. So let me write it that way with set notation. So apologies for changing my mind on how to say this, but saying that X is an element of A union B is equivalent to saying X is an element of A or X is an element of B. Saying that X is an element of A intersect B is logically equivalent to saying X is an element of A and X is an element of B. So if we have Venn diagrams here, we have A, B, we have A or B. The union is like that. We have A, B, A intersect B, looks like this. But we're going to start off talking about sets that are what we call disjoint, that have no intersection, where I have A here and I have B here. So it's easy to add these together, that A or B is just add those two circles together because they're disjoint. I can't add things, I can't have ands with things that are disjoint because there's no intersection between them. So we're going to talk about those basic principles of logic and sets and unions and intersections. We're just going to call them the addition principle and the multiplication principle today. So we're going to solve counting problems using the addition principle, and we're going to solve counting problems using the multiplication principle. In probability theory, an outcome is a possible result of an experiment or trial. In probability theory, an event is the set of all outcomes of an experiment. So we have a probability of an event E, and that is a specific outcome that we are looking for out of all the possible outcomes, called the sample space. And disjoint events cannot happen at the same time. Another word for them is that they're mutually exclusive. They have no intersection. They look like these circles, A and B up here. So the addition principle states that if an event can occur in A different ways, A outcomes, and a second event can occur in B ways, B outcomes. So A and B here that are separate, and both events cannot occur at the same time, A and B are disjoint, then there are A plus B ways or A plus B outcomes for the first event and the second event to, or the second event to occur. Make sure you say or here, first event or the second event, because this is a union, so it gets an or. So the addition principle applies when only making one selection. So again, we don't want to use this very basic addition principle when there is an intersection. We're going to see a problem later where there is an intersection, and we're going to have to not count the intersection twice. So right now we've got 7 red and 5 green marbles that are in a bag. How many marbles are there to choose from? Well, there's 7 plus 5 is 12. So there's that. We've got the set of -5, -3, -1, 2, 3, 4, 5, and 6. So how many ways are there to choose a negative number or an even number? So negative numbers, 1, 2, 3. Then there's no even negative numbers. So then there's 2, 4, and 6. So there's another 3. 3 plus 3 is 6. Student is shopping for a new computer. He's deciding from 2 desktop computers and 3 laptop computers. What are the total number of options? 2 plus 3 is 5. Very simple problems here today. And you see that all that work was done there for you as well. So solve the counting problems using the addition principle. There's 10 red and 6 green marbles placed in a bag. How many are there to choose from? 10 red plus 6 green. There's a total of 16 marbles in the bag. Let A be the set -5, -3, -1, 2, 3, 4, 5, 6. How many ways are there to choose a positive or an odd number? So all the positive numbers, 2, 3, 4, 5, 6. There's 5 positives plus. Now watch out because there's some odd numbers that I already counted, but I'm not going to count them again, right? So 1, 2, 3 are all odd numbers, right? But I don't want to count 3 and 5 again because I already counted them as positive numbers. So there was an intersection here. So there's a total of 8. So if we were looking at positives and we were looking at odds, and then in here are positive odds. So let's see, positive numbers were 2, 3, 4, 5, and 6. And then there was a -5, and there was a -3, and there was a -1. And if I want the union, I want these 3 plus those 2 plus those 3 is a total of 8. So we didn't do anything with the intersection, but the formula tells me to take all of these 5 plus all of these 5 minus those 2 that I counted twice. 10 minus 2 is also 8. So we didn't talk about that where there was an intersection, but that is your general rule for an or a union. Okay, a young boy is deciding on a snack for the afternoon. He is deciding among 5 different types of chips, 3 different kinds of fruit, and 2 different vegetables. What are the number of snack options, assuming that he's only making one choice? 5 plus 3 is 8, plus 2 is 10. The multiplication principle states that if an event can occur in A ways and a second event can occur in B ways, and the first event has occurred, then the second, then the 2 events can occur in A times B ways. This is also known as the fundamental counting principle. So this is assuming that the events can both happen, that they're not mutually exclusive, right? So the multiplication principle applies when we are making more than one selection, A, then B, right? So Diane packed 2 skirts, 3 blouses, 2 sweaters. For a business trip, she will need to choose a skirt and a blouse for each outfit, then decide whether to wear a sweater. Just say, you know, she's going to pick a sweater with each outfit as well. So say that she needs a skirt and a blouse and a sweater. So no sweater is not an option, even though the way that they stated it, there should be 3 options to have sweater 1, sweater 2, or no sweater. But that's okay. They just want you to say outfits are skirt and blouse and sweater, and they want you to multiply all those three things together. 2 times 3 is 6, times 2 is 12. If you had interpreted no sweater to be a third option, then it would be 2 times 3 times 3 would be 6 times 3 is 18 different outfits, because she has to wear a skirt and blouse, but she doesn't necessarily have to wear a sweater. Okay, a restaurant offers a lunch special that includes an entree, a main dish, and a beverage. An entree is a main dish, but okay. I think they meant an appetizer, a main dish, and this is probably supposed to be an appetizer. A main dish and a beverage. There are 3 types of appetizers. Four main dish options and 5 beverage choices. Find the total number of possible lunch specials. So we're going to have 3 appetizers, 4 main dishes, 5 beverages. 3 times 4 times 5 is going to be 60. Yeah, that's right. 3 times 4 is 12, times 5 is 60. Next semester, you're going to take 1 science class, 1 math class, 1 history class, and 1 English class. According to the schedule, you have 4 different science classes that you're eligible to take, 3 different math classes you're eligible to take, 2 different history classes you're eligible to take, and 3 different English classes that you're eligible to take. Assuming no schedule conflicts, how many 4 course selections can you make? So there were 4 science classes to choose from, 3 math classes, 2 English classes, and 3 history classes. 4 times 3 is 12, times 2 is 24, times 3 is 72. D, how many license plates consisting of 2 letters followed by 4 digits is possible? Remember that the digit 0 is included here, so there's 10 digits possible. There are 26 letters in the alphabet. So for each letter, we have the possibility of 26 because it doesn't matter whether the letter is repeated. For each digit, we have 10 because it doesn't matter whether the digit is repeated. So 26 times 26 times 10 times 10 times 10 times 10. And I'm just going to assume that this is correct, is going to be 7,760,000. You can do that on your calculator to make sure that they got that math correct. So how many 2-letter strings, the first from set A and the second from set B, can be formed from the sets B, C, D, and then the set A, E, I, O, U? So we have 3 times 5 is 15. There's 15 2-letter words that can be made there. If you have 3 types of meat to make a sandwich, turkey, roast beef, and ham, and 2 types of bread, wheat and rye, how many different sandwiches, each with only 1 kind of meat, can be created? 1 type of meat, 1 type of bread, right? So we're not making Shaggy Snacks or whatever. If you've seen Scooby-Doo, you're not piling on the meat and bread. So we've got 3 types of meat, 2 types of bread. We've got 6 different sandwiches that we could make from that. Next semester, you're going to take 1 science class, 1 math class, 1 history, and 1 English class. According to the schedule, you have 4 science class options, 3 math class options, 2 history class options, 3 English class options, assuming no schedule conflicts. How many different 4 course selections can you make? 12 times 2 is 24, times 3 is 72. The Missouri license plates have 3 letters and 3 numbers. 3 letters, 3 numbers. That. How many are possible? So I am going to pause while I calculate that. Okay, so there should be 17,576,000 options here for license plates just in the state of Missouri. If they have 3 letters followed by 3 numbers, this is assuming that you don't throw out any special ones. And this is not including any vanity plates that may not follow that rule. So you can see that there's millions of options in each state, and that's what they want just by having something that's as simple as 3 letters and 3 numbers. So that is it for today. Other things that you are going to want to know how to do, though, that are important are going to be if you want to make choices without replacement, you're going to want to know the idea of a factorial. So I'm just going to talk about a factorial right now. A factorial is the idea of, let's say, 5 factorial, and it gets written with an exclamation point after that, is 5 times 4 times 3 times 2 times 1. That's going to be 120. So then 6 factorial, for instance, would be 6 times 5 times 4 times 3 times 2 times 1. So it's going to be 6 times that 120 is going to be 720. And they just grow really fast. So these are important part of this fundamental counting principle, because if I, for instance, said that I needed to pick a 4-digit PIN number, but I wasn't allowed to use the same number in my PIN number twice. So 1, 2, 3, 4, my first digit of my PIN number, I have 10 choices, then 9, then 8, then 7. So this is 90 times 8 times 7 is 720 times 7. 0, 14 is 50, 40. So lots of options, right? Even without repetition there, that if you needed to have a 4-digit PIN number without repetition in your PIN number, you would still have 5,040 choices for what that PIN number would be. Be hard to break that by brute force. However, if you were allowed repetition, it would be kind of silly to choose the same number 4 times, but you could do it. You would have 10 to the 4th power is 1, 2, 3, 4. You'd have 10,000 options. You'd have almost twice as many options if repetition were allowed here as if repetition were not allowed. Okay. We'll come back and we'll talk about this idea of factorial again in the next video when we talk about the binomial theorem, because we're going to talk about something called combinations. And so combinations have a formula, n things, choose r of them, which order doesn't matter. It's going to be n factorial over r factorial times n minus r factorial, like that. And we do not want to calculate this by hand. I'll just do it by hand now. Let's just say that I had 20 students in the class, and I wanted to choose a committee of 5 people to represent the class. So that's going to be 20, 5, and then that's going to be 15. So I'd get 20 times 19 times 18 times 17 times 16 times 15 factorial. There's a 15 factorial that's here that's going to cancel out. There's a 5 times 4 times 3 times 2 times 1 here. This 5 times 4 is that 20. 3 times 2 is 6. It goes into there 3 times. Forget about that 1. So we're left with 19 times 17 times 16 times 3. I'll leave that for you to figure that out in your calculator, or you can give me just 1 second and I'll figure it out in my calculator. So we're going to come back to 15,504 for our answer there. So there's 15,504 ways to choose groups of 5 people where everyone is equal on the committee out of a group of 20 people. That's a lot of choices, right? So, and then as this number gets bigger, there may even be more choices. We'll talk about that a little bit next time and see how it works, but this is going to play into the what we call binomial theorem, which is if I have x plus y raised to the n power, this n choose r is going to be part of that big formula for that. And we don't want to calculate the coefficients of this binomial expansion by hand. So we're going to use something called Pascal's triangle next time to help us with that. All right, I'll see you in the next video for the binomial theorem and Pascal's triangle.